Hello, this is Mr. Sweeney's AP Physics C class, video 4.9 on Atwood machines. And we're going to today discuss Atwood machines, which is a simple laboratory setup used to test Newton's second law. An Atwood machine is a system of two masses connected by a light string of negligible mass hanging from a pulley of negligible mass. Atwood machines are used to test Newton's second law, and gravity acts on both masses in an Atwood machine setup. Between the two masses, which are stretched over the pulley, tension is acting on a string connecting both scenarios. And here you can see a diagram of the Atwood machine setup. We have our pulley that has a string stretched over it, two masses, mass 1, mass 2. And the second mass here is heavier, has more mass than the first mass, so it will drop while the first mass will rise. Next to each mass, I've drawn free body diagrams of the masses themselves. For mass 1, we have mass 1 times gravity downwards and tension pulling upwards. For mass 2, we have mass 2 times the gravity, and we have tension pushing upwards as well. The tension between these two lines is the same. So let's go over the steps in solving an Atwood machine problem. The first thing you have to do is to identify a positive direction. One mass rises, the other one's going to fall. The system moves in one direction as a whole, even though from our perspective the two masses are moving in different directions. That's not the case. They move together as a system, and by convention we'll say that the direction the system is moving in is the positive direction. So as mass 2 falls, it's moving in the positive direction. As mass 1 rises on the diagram, we're moving in the positive direction, even though from looking from the exterior at the problem, mass 2 and mass 1 seem to be moving in different directions. They are moving as one system. Once we've identified a positive direction, we need to determine the net force acting on the system. That's equal to the net force sum of all the vertical forces acting. Once we have that, we can determine the acceleration of the system using the combined masses of all the moving objects. So there's going to be some net force acting on it, and that's going to be due to the imbalance of the forces there. It's going to cause that system to accelerate, but all pieces of the system, both masses will contribute to the mass that we determine here. And finally, not every question asks this, but the tension in the line can be determined if you did a free body diagram of any of the individual masses once you know the net force acting on it. So let's go over an example of this. Here I have an example of an Atwood machine, and I want to determine the acceleration of the system and the tension in the line shown below. Because the 5 kilogram mass is larger than the 3 kilogram mass, this system is going to have a positive direction where the 5 kilogram mass is falling and the 3 kilogram mass is rising. So that means every time I look at the 5 kilogram mass's perspective, down is positive and up is negative. Every time I look at the 3 kilogram mass's perspective, up is positive and down is negative. So they move together in one positive direction. So let's find the net force of this. This is the net force of all the masses and accelerations acting here. And this net force is due just to gravity. From the 5 kilogram perspective, it's moving its mass times acceleration due to gravity. In the 3 kilogram, it's its mass times acceleration due to gravity. In the 5 kilogram example, that gravity is pointing downwards, which is its positive direction, so it's positive. From the 3 kilogram perspective, gravity is pointing downwards, which is its negative direction, and that's why we subtract the second part from it. Plugging in those numbers, we find the net force equals 5 kilograms times 9.8 meters per second squared minus 3 kilograms times 9.8 meters per second squared, and that yields us a total net force for the system of 19.6 newtons. So this 19.6 newtons is what's going to drive our system forward. Using that information, we could find the acceleration of the string. or the system, which is one of the things we were looking for. And we can say that the acceleration is equal to the net force divided by mass. Note that we use the mass of the total system because both the 3 kilogram mass and the 5 kilogram mass must move, and they both have their own inertia. So the 19.6 newtons causes our 8 kilogram system to move and accelerate at 2.45 meters per second squared. And that answers our acceleration issue. Once we understand the acceleration issue, trying to find the tension that's acting in this is as simple as isolating one of these two. And I'll choose to isolate the 5 kilogram mass object. And then drawing a free body diagram, gravity acting downwards on it, and tension acting upwards on it. I can solve this for the tension. So my net force on the 5 kilogram object is its mass, 5 kilograms times 2.45 meters per second squared. That's its acceleration. That gives me a net force of 12.3 newtons. If you looked at the gravitational force acting on it, it's just mass times acceleration due to gravity, and that yields us a gravitational force for the 5 kilogram object of 49 newtons. So I have 12.3 net downwards, 49 newtons downwards from gravity, and I can put those on my free body diagram. So mass gravity, 49 down, net force 12.3 down, tension is just the difference between them. My net force is equal to my mass times gravity minus the tension. So how hard gravity is pulling down minus how much the tension of the line is pulling it back up. It's 12.3 equals 49 minus T, and that gives us a tension in the line of 36.7 newtons.